السلام عليكم ورحمة الله وبركاته. محاضرتنا اليوم هي مادة الباور سيستم أناليسيس، طلاب المرحلة الرابعة جامعة التكنولوجيا قسم هندسة كهروميكانيك. الموضوع هو Unsymmetrical Faults Single Line to Ground Fault. يلقيها على مسامعكم دكتور غسان عبد-الحسين بلال. So let's define the asymmetrical fault. Let's know what does it mean asymmetrical faults. So the asymmetrical fault that mean imbalance condition when the system is be in that disturbance or something is happened. So you will see there's imbalance condition here. Okay, so the voltages and the current become unstable, okay, or unbalanced. So after the fault happened. So when the system is steady state stable, for example, when you have at home and then the electricity is stable, there is no shutdown or cut off. So that means the system is stable. When something happened, for example, there is shutdown. Okay, the electricity is shut down. Okay, that means there's something happened. That means is a fault here, happened fault. So the system is going to be unbalanced. Also, these faults where it's gonna be occur? They're gonna be occur on the terminal of the voltages. Okay, so you have this figure is a complete system. So you have a power plant, transformer, transmission line, substation, step down transformer. You need to upload and then transfer it and then down the transformer to the voltage and distribution network. So this figure is taken from this also. So maybe this fault happened at any point of this, any component of this power system, complete power system. Okay, so the fault, maybe the fault is taken with a pole short circuit. So the fault, let's define the fault like this. Okay, so this is the fault, this is ZF. So the ZF sometimes is going to be 0 if I said voltage short circuit, or sometime with a value. So the impedance, it has value. So the fault through ZF equals 0, okay, or through 0 is as a value. So if a ZF equals 0, that means the voltage short circuit the fault. So so the asymmetrical fault has classified in 3 types. So let's see in this figure. So this figure shows you the faults. So the fault here, see, this is one of the phase that cut. So something happened, there is losing or something, and then this phase is cut. So make it a disturbance for the signal. So the classify of the asymmetrical faults, we have 3 types: single line to ground fault, line to line ground, and double line to ground. So we're gonna, in this lecture, we're gonna focus on this, okay, which is single line to ground fault, and we're gonna explain the formula of this, how to calculate it, and so on so far. So the single line to ground fault, so occurs on phase A. See this figure. Okay, so you have a 3 phase A, phase B, phase C. So the fault happened at this point F with a ZF. Okay, and other 2 phases gonna be 0. So I phase B 0 and phase C 0. So for the boundary condition for single line to ground fault, IC equals 0, and then IA, it has a value. So if the voltage short circuit ZF equals 0, and then VA is going to be 0. Okay, so the sequence current, as I explained in the previous lectures, so this is the matrix that represents the sequence current, which is the sequence current IA0, IA1, IA2, and this is the matrix, and this is the phase IA, IB, IC. So we put 0 here because the B and C is 0. Okay, so we're going to solve this by multiply the row by column, which is 1 by this plus this by this plus this by this, and then you will get this equation, which is the sequence current equal quarters 1/3 to the phase, to the fourth phase. Okay, or IA, which is equal 3 IA naught or IA1 or IA2. Also for the phase, for the voltages, the same sequence VA naught, VA2, VA1, VA2 equal the fault of at phase A multiplied by 3ZF IA1. To solve this equation, so we add this. I'm going to show you in the circuit for the single line to ground fault. So the VA node, which is this the drop voltage, VA1, it has a source, so it's different just EA. And for the negative is the this drop voltage equal. This equation is going to be here. So by rearranging this equation, you will get this is the important formula for the single line to ground fault. So the sequence current, if you calculate it, you will calculate the fault current at phase A. So the VF, that's the voltage at the point F. And Z0, Z1, Z2, which is the zero positive and negative impedance, and 3ZF, which is the impedance at the fault. Sometimes this part is zero because the fault is short circuit, as I mentioned in the previous slide. So this is the circuit of the single line to ground fault. So you see we have three component, which is the positive, negative, and zero. So the positive, it has source, except the positive has source. Negative and zero doesn't have a source. That you, when you calculate the drop voltage for this circuit, which is VF equal Z1 IA1 plus VA1. So to calculate VA1, you need to move this here. So VF, you need to move this here. So VF minus Z1 I1, as you see in this equation. For the Z2, the same, which is there is no source, so the the VF is going to be 0 equal Z2 IA2 plus VA2. So you will get this. And for Z1 is the same. So this is faulted with what? With the value of ZF, so that 3ZF. If you see, this is the drop voltage I mentioned in this circuit. Okay, so this is really three important voltages, sequence voltages. You can calculate from sequence voltages the phase voltage for the single line to ground fault. Let's take example. Quick example. So you have single phase occur at phase A. Okay, so the S base is 30, 11, and start connected three-phase generator. Then a generator is operating at no load. Okay, here, so at rated terminal voltage has sub-transient reactance of 0.5 per unit and negative zero sequence reactance 0.3 and 0.08 per unit respectively. Assume that the generator in neutral is grounded through a reactance of a 5 ohm. So calculate the current that you want to calculate the current and phase voltage. So how are we going to calculate the current? So we need IA, right? So IA, how to calculate? So IA equal 3 IA naught or IA1 or IA2. Okay, so you need to calculate IA naught in order to calculate IA. How are you going to calculate IA naught? By using this formula. Okay, so that you have a ZF equals 0, so you need VEA or VF is the same. So VF, if it's not given at the equation, you have to assume it's 1 to the angle 0, okay, as I explained before. So Z0, Z1, Z2. How to calculate Z1, Z0, Z2? So you have a 5 ohm, which is actual. You need to calculate the base. The base is KV square over S base. You will get you will get the base. This is base, Z base. Okay, and this is actual. So the actual divided by base, you will get the per unit. This is X in per unit for the zero, here. Okay, so multiply by 3 and then add with the zero sequence impedance, which is 0.08. So you will get Z naught. This is Z naught. For Z1 given 0.5 and for Z negative 0.3. So you have a 3 impedance. Now we have to apply on this formula to calculate IA1. So we put this value here, and you have VF or EA, and then you will calculate IA, which is the same IA not IA2. Okay, from this you're going to calculate the current, fault current, which is by 3 IA. So multiply by 3 you will get. So this is in per unit. To calculate it in base, you need to apply this formula, which is S base 2 to 3 multiplied by V base. You have S base, you have V base, and then this is the base multiplied by the per unit. You will get this is actual value for base. Now, for the voltages, as I said, you have to calculate the sequence voltages in order to calculate the phase voltages. So by apply these three equations, so just you have this and you have this, just add them to the formula. You will calculate. You will get the three voltages. Put this in the part of the phases, because VA, VB, VC is the phases that you want, and this is the sequence, and this is the matrix. This is sequence matrix. Okay, and then multiply row by column, you will get this. Row by column, you will get this. Row, and this A, as I mentioned, is 1 to the 120. So thank you so much. If you have any questions, please let me know by email or call me or anything. Can you reach me? Thank you so much.